Hi there. In this video, we're going to talk about the Cauchy-Goursat theorem, also known as Cauchy's integral theorem. We commenced by writing the integral of a complex variable as we had done in the last video. We had some complex function of z equal to u plus jv, with the real and imaginary parts being u and v, both functions of z, and we had a differential change in the complex variable z made up of differential parts dx and dy. We then saw when we write the integral of fz dz, we have to combine these things. We write the integral of fz, we substitute in u plus jv, and we have dz, and we plug in dz, that's dx plus j dy. And once we expand all of this out and we combine some of the terms, what we get is the line integral around a certain path, u dx minus v dy plus j v dx plus u dy. So what we have considered so far is just integration around one path. We have 2 points, maybe A and B, and we have integrated along one path from A to B, and we had seen that this was a line integral. So now we're considering the case where we're going to integrate along a closed path, okay? A closed path. So that means we integrate fz dz firstly from A to B, and then from B back to A. So what does this look like? Well, we use our same line integral that we had derived, and all we now consider is the integral around a closed path. So what we're saying is we're going to evaluate this entire real part, u dx minus v dy, as the line integral around this closed path, and we're going to do the same thing with this imaginary path. So this line integral of fz dz is actually just equal to this line integral of this real part u dx plus, minus v dy, and then plus j, and this integral circulation of v dx plus u dy. So that is it. So what's the next step? The next step is that we are going to take this line integral that we have just derived around this closed path for both this real and imaginary, and what we're going to do is apply Green's theorem to it. So if you want to revise what Green's theorem is, you can go back to the previous videos in multivariable calculus and revise that. So I had done videos on this. But what Green's theorem is that it says if we have the integral around a closed path C, and it's made up of p dx plus q dy, what we can say that is that it's also equal to a double integral around this region, the area between this inside this closed path, of dq dx minus dp dy. And since it's a double integral, we'll have dx dy. So what Green's theorem allows us to do is take a line integral and convert it into an area integral. So why we use that is that sometimes it's easier to evaluate the line integral, and sometimes it's easier to evaluate the double integral. So this allows us to go between the two. So what we can do is now we can apply Green's theorem to this real part of this integral and to this imaginary part of this integral. So let's do that. Let's just zoom back in. So we have the line integral around a closed path of u dx minus v dy. And if we apply Green's theorem, we're saying it's the double integral around some region of dq dx. So here q is equal to minus v. Okay, rather let's write p first. So here p is equal to u p dx, and q is equal to minus v. So we have dq dx. So we have minus dv dx, since that's what q is equal to. So we have minus dv dx, and then we have minus dp dy. So p is u, so we have du dy and dx dy. So let's write this for this other integral as well. So we have v dx plus u dy, line integral closed path of v dx plus u dy, and this is equal to this double integral around this closed region of p dx. So here p is equal to v and q is equal to u. So we have dq dx, so we have dv dx minus dp dy, so we have minus dv dy. Sorry, this should be a u here. So dq dx and q is equal to u, so we have du dx, and then dp dy and p is equal to v, so we have dv dy. So what are we going to do with this? What is the whole point of this? How does this help us? Well, this double integrals actually become zero, okay? How do they become zero? Well, we can see that they are zero if we consider the Cauchy-Riemann equations. So we had derived these equations in one of the previous videos in the series. So I encourage you to go and have a look at how they are derived, but we're just going to use them here. So the Cauchy-Riemann equations said that du dx is equal to dv dy. And the second equation was that dv dx is equal to minus du dy. So if we bring this dv dy to the other side, we get du dx minus dv dy equal to 0. And if we do the same to the other side, for the second equation, we take dv dx to the other side, we're going to get minus du dy minus dv dx is equal to 0. So let's look at this. Du dx minus dv dy. What do we have in this double integral? Du dx minus dv dy. So we can see that this thing is 0. So if this thing is 0, this entire double integral is 0. And it's the same here. We have minus dv dx minus dv dx minus du dy. So quite perfectly, this whole thing all simplifies to 0. So what does this mean? It means that if we look at this line integral of fz dz, if this part is equal to 0 and that part is equal to 0, which is what we have just shown, it must mean that this line integral is equal to 0. We can write that as a result. So this result that we have seen now is that if we take the line integral, in other words, around a closed path, the line integral around a closed path of c of some function z dz, and it's an analytic function, also known as a regular function, which we discussed also in previous videos, we see that it's equal to 0. So this is what is called the Cauchy-Goursat theorem. Also known as Cauchy's integral theorem. We can also apply this to a simple example just to see it illustrated. So let's just take a path. There we have A and we have B. And B is the point 1 plus j0. And then we can also have C. And C is the point 1 plus j. So let's consider a path where we go from A to B, and then B to C, and then C to A. So what function are we considering this for? We can say that maybe f of z is equal to z squared. And what we want to evaluate is this line integral around this closed path of fz dz. So this line integral around this whole curve C, or rather this entire path C of fz dz, so that's going to equal to the integral from A to B fz dz, then plus integral from B to C fz dz, and then finally the integral from C to A of fz dz. So how we're going to apply it is by using this line integral that we had derived earlier in terms of u and v. So we have this integral around C closed path of f of z dz. Let's just write it out again. This is equal to this line integral around this closed path of u dx minus v dy plus j line integral closed path f of z dz. And then we're going to apply this to AB, BC, and CA. So let's just find what u and v are. So we have f is equal to z squared. So let's write that here. So we have f of z equal to z squared. So this means that it's equal to x plus jy squared, because that's what z is. So then that gives us x squared plus j 2xy minus y squared. So what this means is that u is equal to, if we gather everything across here, so we have x squared minus y squared, we gather the real part, and then we have plus j 2xy. So that's what v is. So that's what u is, and that's what v is. So u is equal to x squared minus y squared, and v is equal to 2xy. So we can substitute all of these things inside this equation. Okay, so this is what we actually need. So we have the integral around C of u dx. So u is equal to x squared minus y squared times dx, then minus v is 2xy dy. Then we have plus j, and we have so we can put in what this integral was equal to as well, and that was equal to v dx plus u dy. So let's just put that in. So that's v dx plus u dy. So v, we have 2xy times dx, and we have u, that's x squared minus y squared dy. So let's apply this to the path AB. We can see that for AB, well, there's basically no change in y, and of course y is equal to 0 here. So that's the first thing we can note. We can note that y is equal to 0. So this implies that dy is also equal to 0. What this means, if we now apply this for AB, we take line integral of AB of fz dz. That's going to equal to, well, firstly, this entire term will disappear because dy is equal to 0, and so will this term because y is equal to 0. So what that means is that we're going to integrate from 0 to 1. That's our first boundary of integration for x. And we're going to have x squared minus y squared, y is equal to 0. So all we're going to have is x squared dx, and dy is equal to 0, y is equal to 0, and dy is equal to 0. So this is the only term that we have. And if we integrate that, we're going to get 1 over 3 x cubed, 0 to 1, and that gives us 1 over 3. So we can now do it for b to c of fz dz. And that's going to essentially also be the integral from 0 to 1. But now what we're going to do is we're going to consider it, let's write it. So before we go there, let's note some points about the path BC. So for BC, we see that x is equal to 1, and that means that there's also no change in x at this point. So for BC, it means that x is equal to 1, and therefore dx is equal to 0. So if we consider line integral for BC, we have to integrate with respect to y. So y goes from 0 to 1. So dx is equal to 0, so that term won't be there. So let's consider the second term. We have minus 2xy. Y is going from 0 to 1, and we have minus 2, well, x is equal to 1. So we have essentially minus 2y, then dy, then plus j. Again, y is going from 0 to 1. Dx is equal to 0, so that's not going to be there. And then we have x squared minus y squared, x is equal to 1. So we have 1 minus y squared dy. And if we continue with this, then we see that we get minus y squared, if we integrate minus 2y, going from 0 to 1, and then plus j. Integral of 1 is just y, and integral of y squared is minus 1 over 3 y cubed. Also going from 0 to 1, and if we substitute in 0 and 1, then what we get is minus 1 plus j. Then we have 1 minus 1 over 3. So 1 minus 1 over 3 is just 2 over 3. So that's what the integral of BC is equal to. And then lastly, we need to do the third part. That's from C to A. So what are some observations about C to A? Okay, we're going along the line y is equal to x. Okay, that's 0, that's 1, and both x and y are equal to 1 here. So the equation of the line is y is equal to x. So y is equal to x, then that means that dy is equal to dx. So we can carry on with this expression, and we can write it. So we substitute in dx for dy, and we substitute x in terms of y here, and we can proceed with this integration. If we do that, we get the integral Ca fz dz. So that's going to equal to integral, well, it's going from 1 to 0. So what we can do is we can take the integral from 0 to 1 and reverse it. So instead of writing 1 to 0, we just write minus 0 to 1. So we have x squared minus y squared, y is equal to x. So x squared minus x squared is equal to 0, so that term won't be there. Then we have minus 2xy, so y is equal to x, so we have x times x, that's going to give us x squared, and then dy is going to equal to dx. So we'll have minus 2x squared here, and then with regards to the j part of it, then we have y is equal to x again here, so we have x times x, that's going to give us x squared, and x squared minus y squared is going to give us 0. So that term will come out, and that term will come out, and then we substitute for x and y and dy here. And when we do that, what we get is the integral of 2x squared dx plus j, again reversing the order of integration, 0 to 1 minus 2x squared dx. Sorry, there's a minus here as well. So the minus and the minus is just going to give us a plus. We can just remove both the minuses. So proceeding with this integration, we have 2 over 3 x cubed, 0 to 1, and then minus j 2 over 3 x cubed, 0 to 1. So what we then left with is 2 over 3 minus j times 2 over 3. So if we now add this integrals of a to b plus integral from b to c, and then lastly from c to a, then what we're going to get is, well, a to b was 1 over 3, and then b to c was minus 1 minus j2 over 3, and finally ca was 2 over 3 minus j2 over 3. So substituting all of that in, we get 1 over 3, then minus 1 plus j2 over 3, and then lastly plus 2 over 3 minus j2 over 3. So 1 over 3 plus 2 over 3 is 1. 1 minus 1 is 0. And then we have 2 over 3j minus 2 over 3j. That's also going to give us 0. So we can see that this whole thing becomes 0. So we have shown that if we have an analytic function, we integrate fz dz around a closed path, then we get 0. So this is what the Cauchy-Goursat theorem is, also known as Cauchy's integral formula or Cauchy's integral theorem. So thank you very much for watching.